Let's have a look at what you need to do in order to make a truly scalable shared memory system. Bus-based snooping is good. It's easy, relatively easy to implement, but it has its limitation in terms of scalability. Some people believe that it's not possible to actually build a scalable shared memory system. It is. You just have to do all the tricks of the trade and make a maybe hierarchical cache coherence, or use plenty of tricks when it comes to directory-based cache coherence. So this will mostly look at directory-based cache coherence. The way to make a parallel computer scalable is to make it distributed somehow. So you need to break up the memory and distribute the memory and the processors or the cores somehow, and with some kind of general interconnect. And next lectures we will look more, in future lectures we'll look more on various kinds of interconnects. In the early days of multiprocessing, when a processor only had one core, this was sort of a kind of reasonable or usual way of building machines. It's called UMA or SMP, Uniform Memory Access, or shared symmetric multiprocessing. SMP is not shared memory processing, it's symmetric multiprocessing. Here you have processes and the caches connected with some kind of network with memory on the other side. Drawback here is that you have to pass the network to go to the memory, so you have pretty long latency for every miss in the cache. An alternative, which is actually basically the design that most sort of high-end PC architectures with multiple processors use today, is the NUMA, or non-uniform memory architecture, where you have the processor, and in modern day processors this is a multi-core processor with multiple cores, but still a processor. And then you connect some part of the global shared memory which is close to that processor, and then you have an interconnect, and then you have the other nodes. So if I draw a picture of a modern day system, you have a processor which is a multi-core processor. It has part of the DRAM, and then you have multiple of these with parts of the DRAM. Let's say we have 4. And then they are connected with networks typically looking like this. So most sort of high-end processors, they have at least 2 or even 4 links called, in case of AMD processor, it's hypertransport, or if it's an Intel processor, it's called QuickPath. These are just marketing names of basically the same thing. These are more or less broadcast mechanisms that let you implement coherence across all processors, but you're more or less limited to 4 processors. But each of these can have up to 12 cores typically, so you still have a significant number of total cores in the system. So this is a NUMA system. Just for out of personal interest, we also include something called a COMA architecture, or a cache-only memory architecture. In this kind of architecture, the memory, it looks very similar to NUMA, and it is, but the memory here is not normal memory. It's kind of a big DRAM cache, so called attraction memory. Therefore, it's written AM here. So the idea is that when a processor reads a value, you will attract it to the local attraction memory, and then you may have multiple copies of a cache line in several DRAM modules. There was a trial of making this a commercial processor in the 90s, I guess. but it failed for various reasons. The overall cache coherence mechanism to make build a scalable system is directory-based snooping. So directory-based snooping, you attach a directory next to a memory block, and this directory will contain information about who has a copy of this cache line, right? And when you have a thread that performs an access, you will go, and you have a cache miss, you will have to go to the directory protocol, which will find the appropriate directory. It might be the local one, or it might be a remote one. And you have to look up the directory in contents. The really good thing with this kind of organization is that the interconnect here can be any kind of interconnect. And in particular, it does not need to be a broadcast mechanism. It can be a scalable interconnect that scales the bandwidth up when you add more cores to it. And this is a picture I showed before. What happens when you want to do an upgrade in a directory-based cache coherence protocol system? So we have these 3 cores, as we've seen so many times before, and now the thread 2 will do a store. The store will eventually lead to an invalidation request to be sent, and it goes to the directory. The directory will forward the invalidation request to the cache, and only to those caches that have a copy. These caches, and then depending on the protocol, acknowledgements are sent in various ways. In this case, the acknowledgements are sent to the local cache, and then it gathers the number of copies and then sends it back when it's finished to the requester, to the directory, I'm sorry. And then the cache-to-cache transfer works in a similar way. You have to ask the directory because you don't know who's got it, and the directory will forward the request to the cache that has it, who will then forward the data, and then it will send the acknowledgement back to the directory who knows that this is finished now.